Okay, in this video we're going to talk about the second fundamental theorem of calculus. And just a side note before we begin, I'm calling this the second fundamental theorem, and what we discussed already was the first fundamental theorem, but that's not actually standard. Sometimes people will refer to this theorem as the first fundamental theorem and the other one as second fundamental theorem. So it's not standard terminology, unfortunately, but both theorems are very much related to each other, so they're both important theorems. The way I think of the second fundamental theorem is it's really the theorem that you'd want to use if you're trying to take the derivative of a definite integral. So that's what we're going to see here. So, all right, to begin, let's actually just look at the theorem. It says, again, the hypothesis if f is continuous on an open interval from a to b, and if we define capital G to be this new function, so that this is an unusual function, that the input is the upper bound of the integral. So we've got this function. We'll talk about this in 1 second. Let's just finish the theorem. And the theorem says that this function is continuous on that interval, and it's differentiable. And its derivative can be defined. So the derivative of this integral will just be little f. Okay, so that's what the theorem says. Let's make sure we understand what this thing is saying. So the first part of the theorem is we define this function capital G, and it's a function. The input is x, right? It's a function, so the independent variable, my independent variable is x, and where x is the upper bound. So when we look at this integral, it's the integral from some value a to x under the curve f of t dt. So here's our function f of t, whatever it happens to look like. We don't know what it is. But whatever the input of your function is, capital G, we're going to go from a to that input. And the output of this function, it will output the area, the signed area between the curve and the x-axis. It's going to output the definite integral from a to that value x. So we can think of this sort of as like an area function. And basically, what the second fundamental theorem of calculus is saying is that the derivative of this area function is little f itself. Okay, so let's prove this. This is not so hard to prove, actually, and it uses the first fundamental theorem of calculus. So we're going to prove that the derivative of the integral function, we want to prove that that's equal to f of x. So let's evaluate using the first fundamental theorem of calculus. We know that this definite integral, we would find an antiderivative for little f, so we'd call that capital F, and we'd evaluate it at the top bound minus evaluating it at the lower bound. Now when we go to take the derivative now of this thing, we're taking the derivative of the antiderivative of x. So that's going to be little f of x minus the derivative of the antiderivative of x evaluated at a number. So this part is just a number. So when we take the derivative of this number, it's going to go to 0. And thus, the derivative of our area function, the derivative of this integral, is little f of x. So there's our proof. Okay, so that's the second fundamental theorem of calculus. Let's see how we can use this. So let's look at these first two examples. If I go to take the derivative of an integral from pi to x of cosine of t dt, so my little f of t is cosine of t. Oh, cosine of t. So the second fundamental theorem of calculus says that this thing equals cosine of x. Period. I'm done. Now, if that seemed too miraculous and you're worried that you didn't do it correctly, you can always just do it by hand using the first fundamental. So we could take the derivative of, I don't know why I'm writing so crooked, sorry, the derivative, here we go. Do the derivative the long way, which would be to evaluate what's inside this integral. Take the antiderivative of cosine. So the antiderivative of cosine is sine of t. This is right now I'm using the first fundamental theorem of calculus, and I'd want to evaluate that between x and pi. So I would be taking the derivative of sine of x minus sine of pi. The derivative of sine of x now is cosine, and the derivative of sine of pi is just a number, so the derivative of it is 0. And so the long way, we also get cosine of x. Okay, so we could do this problem two ways because we happen to know the antiderivative of cosine. So, but there's no real reason to do that. The second fundamental theorem of calculus would tell us this is cosine. And likewise, the second fundamental theorem of calculus here, so notice that our little f of t is 1 over 1 plus t squared. So the derivative of this integral is just going to be 1 over 1 plus x squared. And again, that's just using the second fundamental theorem of calculus. Again, if you felt like you didn't really believe that and you wanted to use the first fundamental theorem of calculus to prove this to yourself, we could do that. We would have to recognize the antiderivative of 1 over 1 plus t squared. So we'd have to recognize that that is just arctangent evaluated between, arctangent of t between 0 and x. So we would apply the first fundamental theorem by plugging in the bound x minus plugging in the bound 0. So now the derivative of arctan of x is 1 over 1 plus x squared, and the derivative of this constant is 0. So again, we're left with 1 over 1 plus x squared. Okay, I'm going to save the next examples for the next video.